Hello. Today we are going to be discussing number 5 on the AMC uh, 12 Format B 2018. This particular problem, and it is how many subsets of that set you see on screen contain at least one prime number. So, before I jump right into this problem, I'm gonna make some amends because I did mess up once in a video. So, I said mistakenly last time that 2n plus 1 was congruent to 0 in mod 3. That is, of course, not the case, as many of you may have simply put in n equals 1, and were very confused, I'm sure, as to why 1 plus 1 was suddenly divisible by 3. That is actually not the case. I meant for all odd integers in the exponent. That's what I meant to say. I'm sorry. We'll definitely discuss why that works in a later video. It's actually rather interesting. Give me a second. My eraser is not very good. Okay. So, jumping into this question, I'm going to wait a second for those of you who want to pause and give this a try yourself. Okay, so for those of you who just want to enjoy the show, you can, I guess, continue. And we're going to be talking the amount of prime integers in this set. So the first thing I did was underline the original primes in the set, and actually when I was doing this problem for the actual test, I forgot 2 was prime, so I ended up getting the wrong answer, but that's besides the point. So, jumping right on in this problem, I would instantly recall one of the, I guess, one of the, not maxims, but one of the properties of probability, which is this holds true for any probability A such that probability B is the probability of A not happening. And for these probabilities, I realized that it doesn't ask for the probability, but it's still useful when you're talking about how many states. So instead of the P, simply imagine the total number of possible sets minus the total number of sets that only contain composite integers equals the amount of sets that contain at least one prime integer. So, with this property in mind, we're going to begin. And in case you're wondering why we go this route, I will be solving it the other way after I'm done solving it this way, and you'll find that it's just easier. For one reason, mainly because you don't have to worry about overcounting the total number of possible, total number of states that have at least one integer, or one prime integer, because oftentimes you'll get the same exact set for both. Like, let's say 2, 3, 4, 5. If you're counting the total number of sets for 3, then you'll have 2, 3, 4, 5 in it. But then when you're counting 2, you'll also have 2, 3, 4, 5. So you'll have to subtract out those. So it ends up getting a bit more complicated and easier to make mistakes. Okay, so first of all, we need to calculate the total number of subsets. And the definition of a subset is includes the empty set, or the null set. So just nothing. That was an awful bracket. Okay. It includes the null set and the original set, so this is a subset of itself for the sake of this problem. I'm not quite sure what it is in actual set theory, but I'm pretty sure it's something similar. Okay, so to calculate the possible number of subsets of this set, which is P of n, we first what I would like to do is do a simpler sort of problem. So we want to talk about just the set 2 comma 3 and the possible number of states. Not relevant to the contains at least one prime, just the total possible number of states. Well, you can say that it just has 2, right? The subset, just 3 as a subset, nothing, or 2 comma 3 are all subsets, or 4. Now, whenever we see 2 of something and then 4 as a result, I oftentimes go straight to powers of 2, which is perfectly fine in like a fast competition type setting, but it can oftentimes lead to very bad misjudged assumptions and can lead you to get the problem horribly, horribly wrong. So I would take some time here to double check why this makes sense. Well, you can consider the fact that in every set, an element of that set is either in it, in the subset, or not in it. If you consider it this way, you can almost consider it as an on-off switch, or most computer software engineers as just 1 or a 0, or 2 possible states. So you multiply the number of possible states of this, which is simply either there or not in the subset, and the number of possible states for this one, which is either there or not. So you have 2 by 2, or 4. So armed with this knowledge, we're going to go straight to the bigger one. I don't really feel a need to compute other ones, because I think that makes enough sense. We're just going to go straight to this one. There is 8 total numbers in this set. So it would be 2 possible states times 2 possible states. I'm just going to write a few of these out here. All the way to there. Or 2 to the 8th. Or, as many of you are more familiar with the number, 256. Okay, so now we want to calculate the probability, or total number of states, of all composite integers showing up in this set only. And as you'll notice, there are 4 composite integers in this set. And we can use an alarmingly similar method to how we calculated total possibilities of the set. So if we're talking about subsets that don't have prime integers in them, you could say, well, look, the possible states for that, for 2, which is a prime number, for it to be in the set is 0. Like, you can't have any states of it except not being there. So there's 1 state for that. Then for 3, you can consider the same thing. And then for all the prime integers, you can say that they don't have this state of actually being there in the set. Because if they do, then it has at least 1 prime in the set. So you can imagine it as 1 by 1 by 2 by 1 by 2 by 1 by 2 by 2 to the 4th, or 16. And now, just to round out the problem, we subtract those 2, get 240, and get the answer correct. So now, as I said, I'm going to discuss how you might go about doing it the other way, as well as some pitfalls, I suppose. Who knows, it might work out just fine, and I've been under an illusion this whole time. Okay, so right away, we're going to be dealing with messier waters, right? So what I would do is first consider all 2's that go in the set. So for now, we're going to be considering that the 2 has no off state. Okay, the 2 has no off state. Everything else will vary as normal, but the 2 has no off state, which makes a kind of sort of sense. Okay, because that guarantees that in all the sets that we're making, 2 is in them. And you can see why this gets more complicated, because there's also a situation where the set's 2, 7, 8, 9, but then if we do the same thing for 7, you'll have 2, 7, 8, 9, as I mentioned at the beginning of the video. So this would be 2 to the 7th, or 128 for just 2, which is already a bit suspicious, to say the least. But I think we'll be fine here. So the way I would have thought to go about this problem is I would multiply that by 5 and get what? 640. And that's obviously not correct. And if you bothered to watch the last like 9 or so minutes of this video, you'll know that that's off by about 400. So we have overcounted 400 sets. And the reason why you multiply by 5, or sorry, you wouldn't multiply by 5. What am I doing? Okay, you would multiply by 1, 2, 3, 4, because there are 4 of these in there. So it would be 480 plus 32, 512. There was a much faster way I could have calculated that, but whatever. Okay, so now we have 512, which we've overcounted by still quite a large margin. A little over 300, which is still obviously completely wrong. So if you look at the multiple choice that they give, it's nowhere near. So you would obviously reconsider your answer. So what I would do is not tackle it this way, but I would do it in a slightly more interesting way. So, are you all well aware of the handshake problem? Like they say, oh, well, I've got 5 people, how many handshake, and they all shake hands, how many handshakes? Well, how much we've overcounted by here, saying it was 512, is very similar to this. So if there's 5 people, and they all shake hands, well, it would simply be 5 times 5, right? Because there's 5 people, they all shake hands, and we get 25. Perfectly wrong answer. Now, if we would look as to why, well, we're considering every person shakes all the other people's hands, which they can't shake their own hand, so that's already problematic. And when they go around, if you shake somebody else's hand, they're not going to shake your hand back. So we've obviously overcounted. So the way you can remedy this is by saying, okay, well, the first person goes around and shakes the 4 people's hands. But now nobody will shake his hand because he shaked everybody else's hand. So that would be 4 handshakes. Then plus the 3, because then the next person would go around, shake the other people's hands, wouldn't go for the first person, and then you would go down all the way to 0. And you would round that off by saying, well, that's 10, not 25, as we so horrendously overcounted. So this is very similar. Instead of multiplying this by 4, like you might go about doing, then backtrack and subtract a bunch and still probably not get the right answer, you can simply say, oh, okay, 2 to the 7th. Then say, well, now 2 is not in here at all. Because we've already counted all the probabilities that 2 is in here. Now we're going to look at 3 and all the possibilities where 3 is in when 2 is not in. And you can consider, since this guy is always not there, and this guy only has 1, then we go 2 times 2 times 2 times 2 times 2, or 2 to the 6th, which you all know as 64. So then the same thing happens with this guy. He no longer is in the set, and we go to 5. And he only has 1, 2, 3, 4, 5, 6. Or 1, 2, 3, 4, 5. Right? So now we have 32. And then we'd go in with 7. But sorry, we wouldn't go in with 7, because we've already counted all the 7s, because when you think about it, 7's been in every single time. But we still, actually, never mind. We still have to count all the probabilities where 7's just in. So we would count that, which is 1, 2, 3, 4, 2 to the 4th, or 16. And this is where you would add these up. And this is where it's not as efficient as the other solution. Still go whichever way you would like. But as I say, this one has a bit more pitfalls with the whole multiplying business and overcounting. And even when you don't overcount, you still have to add up all these numbers, which, let's be honest, we all can do, because those go to 10, those go to 10, so now we just have 20 plus 120 plus, oh, that's just 100, so 100. So, what, 240? Exactly. So, we could all add this, but it's still, in the end, not as efficient. But that's what problem solving is all about. Finding a solution to the problem, not necessarily a fastest method. So I'll see you all next time.